One thing I'd like to talk about with everyone is the importance of physics and the special role it plays in science and also in science education, but also mathematics education. Physics isn't really like any of the other sciences in the sense that it integrates together mathematics and science. It's really, physics is the mathematical interpretation of the world. So you have observation integrated with mathematical analysis, which is what Galileo used to form the beginning of physics. And just like that was the beginning of modern science, where physics then eventually led to quantum physics, which explained chemistry, and physics and quantum chemistry together explained biology. That is the unfolding that occurred, and quantum physics really and chemistry based on quantum physics really started in the early 1900s, and molecular biology based on both of those combined started in the 1950s. And the problem we face in the United States is that the science sequence was locked in 1892. So when the science sequence was locked in 1892 by the Committee of 10, none of this understanding of the connection that physics, chemistry, and biology was known to that committee. And so it made sense to them at the time, especially in a world where algebra was a 11th or 12th grade elective course. Most people didn't study algebra before they graduated high school. It made sense to them that physics would be something studied only by those who were going to study algebra at the end of their high school career, and it would be subsequent to chemistry and biology, because you don't, and by the way, it wasn't even biology then, it was botany and zoology. And those were all qualitative studies, and the mathematical connections weren't there at all. But what's happened is, as algebra has moved from being an elective 11th or 12th grade course to being a required 8th or 9th grade course, and the second best predictor of whether a student's going to go to college being the completion of algebra successfully by the end of 9th grade. As that move took place, the sciences didn't move with them as they should have. So physics should have moved with algebra into 8th or 9th grade and should be taken at the same time. And that got locked in by a number of things. The textbooks were written based on trigonometry and calculus, because in the US we always taught mathematical physics with one of those two maths. There were no algebra-based textbooks, therefore there weren't the materials. Teachers weren't prepared to teach physics because not many people took it. Not many people majored in physics, therefore there were very few people capable of then becoming a physics teacher. And so this became a very difficult problem for the United States, and one that people really sometimes recognize but have been slow to deal with. I think it's come into more focus of late because there's a big push towards STEM careers, because there are many available jobs open in the STEM fields, and there are very few students who are prepared to take those jobs. And the reason for that is that the number one required course to prepare for STEM careers is physics, and most students don't study physics. So now you've got this real paradox, which is that there's no pathway to create students who know physics, therefore there's no way to solve the problem of STEM careers. And because there's no one with a STEM, there's very few people studying physics in high school, middle school and high school, there are very few people who ever will become physics teachers to go back and teach it to those kids. So it's a bootstrap problem, which is how do you break this cycle of not having enough students with enough background to go on to become the teachers of the future, to create the knowledgeable students of the future. Without that, you end up with where we are now, which is a lot of talk about creating interest in STEM careers, which there is a lot of talk about that, and projects building robots and rockets and doing all kinds of fun things, Project Lead the Way engineering. And if you do successfully get kids interested, they aren't prepared to do anything about it, because if they go to college, they really can't engage in the courses that would allow them to become an engineer, a doctor, a veterinarian, agriculturist. All of these things require physics. In fact, if you look at a college catalog, you'll see that 90% of all of the majors that you would identify as being STEM require physics, and only 20%, for instance, of the students in New York City study physics, which means 80% of those students are going into college really unprepared to succeed in the courses they need. When I was running my pre-engineering program at Bergen Tech, I had a Perkins Advisory Board, which is required if you're a vocational school, and they advised me on my pre-engineering program. And my board I made up of the deans or associate deans of the major engineering schools in New Jersey, Rutgers, Stevens Institute, and NJIT. And I would ask them, what do they want to see as preparation for their engineering schools, which is a good proxy for what STEM careers. And they were very clear about it. They said what kids need to study in order to be prepared for engineering school is AP Physics, AP Calculus, AP Computer Science, and AP Chemistry. They thought Project Lead the Way and projects and building robots was fine, and if it got the kids excited to do those courses, it would be fine. But if they came to the college without having had those courses, it would be a big problem. And that problem is also clear from the fact that half of the students who begin engineering school drop out of engineering school in the first year. And usually that's because they fail physics, chemistry, or calculus, which is exactly why it's in the self-interest of the deans of engineering schools to tell me they want kids who are successful in those subjects before they leave high school, because it doesn't work well for them if they have to replace half their students every year, in the second year. They'd like students to enter who can succeed. So this connection is so strong because physics sort of, if you think of the traditional, all the other sciences as being over here and mathematics as being here, physics really is what connects the two. And physics connects science and mathematics. And by doing that, it gives meaning to mathematics because the kids see what mathematics is good for. And it makes it possible to learn more advanced sciences using the physics that the sciences are based on. We saw that with the high school, where we take algebra-based physics in 9th grade, but we teach, and in doing that, we teach mechanics for the beginning of the year, then electricity and magnetism, then simple harmonic motion, then waves, then end with quantum physics and nuclear physics. So that's the first year. Every 9th grader in the school has a background in electrostatics and quantum and nuclear physics, which is exactly what, and as well as energy and some other things, which is exactly what you need to understand chemistry from the ground up, because then you can actually devise the periodic table instead of sitting around memorizing what's the difference between a compound and a mixture and other such unimportant things. You can actually problem solve and develop what molecule shapes are going to be, all of the interesting parts of chemistry, ending with biochemistry, and then you can begin biology with biochemistry and work your way through biochemistry through the 7 processes that are universal to life on Earth, and then you can start building cells, and then you can take the cells and build organisms, and then organisms can relate to one another, and then you've got ecology. So now you've got this flow that makes sense to kids. They can see how the physics leads to the chemistry, leads to the biology. All along, you progress the mathematics, so you begin with algebra, then you move to geometry, and then to trigonometry, and then to calculus, which parallels what they're doing in physics and what they're doing in the sciences. We're now in the process of taking that same logic and driving it down to kindergarten by taking the next generation science standards and adding a thread of physics in between the science and the math, so that the science is built on what science is being taught that year, the physics is related to what science is taught that year, and the mathematics that's used is exactly the Common Core required math for that year. So just like we got big gains in algebra by having the kids see the use of algebra, we're going to see big gains in 4th grade math when they see that the problems they're doing in physics, they can do only with the 4th grade math. I mean, even going down to kindergarten, if you are 1st grade, if you have a pendulum going back and forth, that's a great chance for kids to count. So counting is a Common Core standard in 1st grade, in kindergarten or 1st grade. They're doing physics then. And then if you, in 3rd or 4th grade, you change the mass on the pendulum and you see that it doesn't change how often it goes back and forth in a minute, now you're actually discovering physics, and you're learning physics in a way that right now even many of our teachers in those grades don't fully understand it. So we think that the solution to really drive the United States forward in science and mathematics is going to be really taking on this one big challenge, which is the lack of understanding of physics and its unique role, and addressing that rather than just recognizing it and then hoping that someone else fixes it later on. Thank you.